Hi everyone. Before watching this, be sure that you have already watched the first 5 videos. So now I will discuss few important questions on relations functions. So relations functions chapter weightage is 1 marks 1 question, 2 marks 1 question, 3 marks 1 question, 5 marks 1 question. Totally it will be 11. I have already discussed this 5 mark question. Now my intention is to cover this 1 to 3 part. So first of all, for 1 marks you may have a question like define binary operation. So in a very easy manner you can define binary operation, that is, for any non-empty set A, star is said to be binary operation on A. For all A comma B belongs to A star B belongs to A. So star is said to be binary operation on a non-empty set A. For all A comma B belongs to A star B belongs to A. The same question may be asked for 2 marks with some examples like, suppose A star B is equals to AB plus 1 on set of real numbers. Verify whether this operation is binary or not. So for any two A and B belongs to set of real numbers, A into B is also real number, plus 1 is also real number. Therefore AB plus 1 also belongs to R. A comma B belongs to R implies AB plus 1 also belongs to R. Suppose they may give like A star B is equals to A minus B. Then on N, this is not a binary operation, because to become a binary operation the condition for all A comma B belongs to A star B should be belongs to A. Here we can give any counter examples. Suppose if you substitute A is equals to 2 and B is equals to 4, then 2 star 4 is equals to 2 minus 4, which is equals to minus 2, does not belongs to N, hence it is not a binary operation. If it is on set of real numbers or set of integers, then obviously this A star B is equals to A minus B is also a binary operation. So next, some operations may be asked for show that is commutative and associative. So commutative means A star B will be given as AB divided by 2. You need to find B star A. So this star is defined as product of first element into second element divided by 2. Therefore B star A will be product of first and second element divided by 2. But we know that AB divided by 2 will be equals to BA divided by 2. Hence it is commutative. Then how to prove associative? To prove it as associative, we need to prove A star B star C is equals to A star B star C. So now what is A star B star C? So what is B star C? So as I have explained earlier, this operation is defined as taking first element into second element divided by 2. Here first element is B, second element is C, divided by 2 we get is equals to. Now first element is A, second element is BC by 2. First of all it will be A into BC divided by 2 whole divided by 2. Therefore this is equals to ABC divided by 4. Similarly we shall find A star B star C is equals to, what is A star B? AB divided by 2 star C. Again first element is AB divided by 2, second element is C. Therefore it is AB divided by 2 into C divided by 2, which is equals to ABC divided by 4. Hence it is commutative. Then I have mentioned one more problem, A star B is equals to 1. So if A star B is equals to 1, then B star A is also is equals to 1, hence it is commutative. Similarly for associative, you can prove this one as A star B star C is A star 1 is equals to 1. Similarly A star B star C is also is equals to 1. Suppose if you have A star B is equals to A, then whether it is commutative? No, because B star A will be equals to B, because this star is defined as getting a first element of that A star B. Here B star A will be B. Whether it is associative, now we shall see A star B star C is equals to A star, here we get B, because B star C is B, is equals to A, and what is A star B star C? This is equals to A star B is A star C is equals to A. Somebody will conclude like if it is not commutative then it will not be associative, but we can't consider like that. We need to check that particular conditions whether it is binary commutative and associative or not. Next, A star B is equals to AB by 4 on set of real numbers. Then find the identity element. So what is the definition of identity element? Identity element is A star E is equals to A. Now A star B is AB by 4. What is A star E? A star E is AE divided by 4 is equals to A. Hence we can cancel A and A to write it as 4. Therefore 4 is the identity element. So then for 3 marks usually a question will be asked on verify whether the relation is reflexive, symmetric or transitive. Even they may ask whether it is equivalence or not. So here I have one R is equals to order pair A comma B, where A less than or equals to B defined on set of real numbers. Then to prove it as reflexive, so carefully observe this particular problem because this is important problem. Reflexive. To prove it as reflexive, we need to assume A comma A. A comma B means A less than or equals to B. A comma A means A less than or equals to A. We know that A less than or equals to A is true statement. Therefore, A comma A belongs to R for all A belongs to set of real numbers. Therefore, it is reflexive. Whether it is symmetric, so we can consider A comma B belongs to R. This implies A less than or equals to B. Then not necessarily B less than or equals to A. So here you can give counter example also, because 2 comma 3 belongs to R, but 3 comma 2 does not belongs to R, hence it is not symmetric. Or else A less than or equals to B, but it is not necessarily B less than or equals to A, hence it is not symmetric. So here you need to add this is not symmetric. Then finally transitive. So for transitive we need to assume A comma B belongs to R and B comma C belongs to R. So A comma B means A less than or equals to B. This B comma C means B less than or equals to C. Obviously this A must be less than or equals to C. A must be less than or equals to C. Hence ordered pair A comma C belongs to R. So similarly we may have one problem like R is equals to ordered pair X comma Y such that X minus Y is an integer. X minus Y is an integer. Then on Z we shall consider this one on Z. Then so first of all for reflexive you need to consider X comma X. What is the definition for X comma X? X minus X is equals to 0. It's an integer. Therefore for all X comma X belongs to R, for there exists for all X belongs to Z, we have order pair X comma X belongs to R, hence it is reflexive. Then we need to consider symmetric. So X comma Y, if you consider X comma Y, then it is X minus Y is an integer. X minus Y is an integer. If X minus Y is integer, obviously Y minus X is also an integer. Therefore ordered pair Y comma X belongs to R. Then finally we have transitive. For transitive we need to take X comma Y belongs to R, Y comma Z belongs to R. So now X comma Y belongs to R means X minus Y is an integer. Let me consider that integer as L. Y comma Z belongs to R means Y minus Z is an integer. I will consider it as M. We need to prove X minus Z is an integer to prove it as transitive. Therefore X minus Z can be rewritten as X minus Y plus Y minus Z. So L plus M, integer plus integer, which is an integer, therefore ordered pair x comma z also belongs to R. So then ordered pair a comma b, a minus b is a multiple of 4. I will briefly explain this. First of all, modulus of a minus a is equals to 0 is a multiple of 4. Therefore, for all a comma a belongs to, suppose it is on z, belongs to z, for all a belongs to z, a comma a belongs to R, hence it is reflexive. Then if modulus of a minus b is a multiple of 4, we can write modulus of a minus b is equals to 4L. Then modulus of b minus a is also is equals to 4L itself, hence it is symmetric. Then finally, to prove it as transitive, we need to consider a minus b and b minus c. If mod of a minus b is a multiple of 4, we shall consider 4L, this one as 4M. If you remove this modulus, we get a minus b is equals to plus or minus 4L, b minus c is equals to plus or minus 4M. Now, to prove a minus c is a multiple of 4, we shall consider a minus c as a minus b plus b minus c, which is equals to plus or minus, I will take 4 outside, then it will be L plus M. If you take modulus of a minus c, which is equals to 4 times L plus M. Hence, ordered pair a comma c also belongs to R because it is a multiple of 4. Hence, it is transitive. Since it is reflexive, symmetric and transitive, it must be an equivalence relation. Similarly, you may give like order pair a comma b is equals to such that a is equals to b on z. Then obviously a comma a means a is equals to a, which is true. And if a comma b belongs to R, obviously b comma a should belongs to R, because here you have a is equals to b, then obviously b must be equals to a, that's also true. Then for transitive, a comma b belongs to R, b comma c belongs to R. You need to prove a comma c, therefore here it is a is equals to b, b is equals to c, hence a must be equals to c, hence ordered pair a comma c belongs to R. Then you may have some problems on show that or verify the given function is 1 1 and onto or not. So here f from R to R given by f of x is equals to 1 plus x square. We need to identify whether it is 1 1 and onto or not. So to prove it as on 1, we need to consider f of x1 is equals to f of x2. Then 1 plus x1 square is equals to 1 plus x2 square. 1 1 get cancels. X1 square is equals to x2 square. Or many times students will write x1 is equals to x2, but x1 is equals to plus or minus x2 since it is defined from R to R. If it is defined from n to n, obviously x1 is equals to x2, hence it is 1 1. But on this R, it is not 1 1 because f of x1 is equals to f of x2 does not imply x1 is equals to x2. Otherwise, you can give counter example also. F of 1 is equals to 1 plus 1 square 2. F of minus 1 is also is equals to 2. Therefore, f of 1 is equals to f of minus 1, but 1 not equals to minus 1. Therefore, this is not 1 1. In examination also, you need to have a gap between this 1 1, because if it is not 1 1, you need to give the heading as not 1 1. Then on to. So for on to we need to assume y is equals to f of x. F of x is 1 plus x square. Our intention is to find the value for x, and therefore x square will be y minus 1, x will be square root of y minus 1. Now you can choose any real number. I will choose y is equals to minus 5. So if y is equals to minus 5, x is equals to minus root 6, which does not belongs to R. Hence, it is not onto function. So similarly, we may prove f of x is equals to mod x is neither 1 1 nor onto. Very simple method. So whenever you are going to disprove, you can give counter examples. But to prove it as, you need to go stepwise. Now I will consider f of 2. F of 2 is equals to how much? Plus 2. F of minus 2 is equals to how much under modulus function? Plus 2. So f of 2 is equals to f of minus 2, but 2 not equals to minus 2. Hence, it is not 1 1. And to prove it as not onto, we shall consider any negative number. Minus 5 belongs to R, but there is no x such that f of x is equals to minus 5. There does not exist any x such that f of x is equals to minus 5, because under modulus function every number, positive or negative, it relates to positive number itself. Therefore, the range will be set of non-negative real numbers. Therefore, here minus 5, not only minus 5, you can choose minus 10, minus 20, minus 2, minus 6 and even. So, for all that values we don't have pre-images, therefore it is not onto. Similarly, we may get the signum function concept. Signum function is also neither 1 1 nor onto, because I will consider f of 2. F of 2 will be 1 because it is greater than 0. Then f of 3 is also is equals to 1 because it is also greater than 0, but 2 not equals to 3. And also range of the function is 1 0 minus 1. If you choose any real number other than that 1 0 minus 1, I will choose 5 belongs to R, but there is no x such that f of x is equals to 5, hence it is not onto. So this function is neither 1 1 nor onto. Then we have one important theorem, that is f from a to b is 1 1, g from b to c is 1 1. Show that GOF from a to c is 1 1. So GOF from a to c means we shall consider GOF of x1 is equals to GOF of x2. We need to prove x1 is equals to x2. Now by definition of the function, we can write g of f of x1 is equals to g of f of x2. Therefore, we can write f of x1 is equals to f of x2. How can we write f of x1 is equals to f of x2? If g of a1 is equals to g of a2 and g is 1 1, we write a1 is equals to a2. In the same manner, f of x1 is equals to f of x2. Since f is also 1 1 function, we can write it as x1 is equals to x2. Therefore, g of f of x1 is equals to g of f of x2 implies x1 is equals to x2. Hence, it is 1 1 function. So, these much are enough for 2 and 3 mark questions on relations and functions.